Okay, so I will start. Okay, hello. So, so today is the last lecture about the statics. Tomorrow we will start the dynamics, and so I will try to make a kind of summary of what we have done. But before to do that, let me finish what we started yesterday. So we wrote the propagator of the. So we were doing the case of a directed polymer in random media. So I told you that this polymer is x of tau, and in general the dimension of the variable x is n. So essentially we looked n equal to 1. Yesterday, I think with Ivan, you did the algorithm applied to the case n equal to 1. Then there is a case n equal to 2, which is also physical, but then you can study the model also n equal to 3 on the Calais 3 and so on. So x is our path, okay? And so actually, I mean, there is a formulation which is essentially coming from quantum mechanics, which is the path integral formulation for the partition function zxt. So what we are saying is, okay, we have paths, so let's sum over all possible paths. Let's fix the starting point and the end point. And now we are looking all the possible paths in the tau, in the time tau. And then we have two terms. We have the elastic term, which is d tau from 0 to t d tau x square. And I like to put a term 1 up, so let me put 2 here. And then the second term is always the same integral, but let me is better to write it like this: is minus 1 over t integral over d tau from 0 to t, and this is the term of the disorder. And I close this parenthesis, and so this is the partition function. And essentially, we have 1 over t, you can take it, and the energy is the sum of the two terms. Now, what I show is that using this way of writing, you can actually use the formula of Feynman-Katz and write the Schrödinger equation for the propagator, okay? So let's say this is derivative over t of zxt is equal to minus h. So let me write this h here is minus t over 2. In general, you have n dimension here. And then the potential is V, so it's exactly what you wrote here. So it's plus Vx tau tau, okay? And this, we close it like this. And this Hamiltonian applies the propagator. And we can say that because all the paths start at the origin, the initial condition is just 0, okay? You start in 0. Okay, so this is the Feynman-Katz approach, and we saw, okay, here you have a multiplicative noise. So this is a difficult equation because usually we are used to the Langevin equation in which the noise is alone and is additive. Here it multiplies that, okay? And then the idea is to say, okay, this is if we look at this Schrödinger equation, we know that it's difficult, because actually the potential depends explicitly on the time. And we are used to potential like this, okay, where it depends only on the position, but now we have the time, and so it's difficult, it's difficult to solve. If it was time independent, the solution will be easier, and this is what we will do today. But before to do that, let me, for your culture, know that I told you that this problem of the polymer in n dimension is actually equivalent to the KPZ equation in n dimension. So equation of a surface of n dimension that propagates. And then to understand that, actually you have to take this equation, the Schrödinger equation, and operate what is called the Kolopf transformation. So maybe this is not very, so I write just a small square here. So this is called Kolopf. And so if you define T as 2 nu, a new parameter nu, the most important change is this one, is that you introduce essentially a new field H, which is essentially the free energy for the polymer. But okay, to be precise, it is this. So H is the log of Z, but with some prefactor. So it's a new field, okay? And now we also define, so this is one change of variable, this is the other change of variable, and the last one is minus Vxt equal eta xt. So it's not difficult. You can just replace everything, do the calculation. You will see it is quite easy. And what you will find is that the equation of motion for this, now H is a scalar, X is a vector, so it is a surface, okay, of n dimension. And this is this equation, nu secondary, so Laplacian of H plus lambda over 2 gradient H square plus eta xt. So this is more similar to what we are used. The noise is additive, is a surface growth, but there is the price to pay is now that is not just a diffusion equation, but is a nonlinear stochastic equation, which is called Kardar-Parisi-Zai. Okay. So essentially, in the problem of the directed polymer, the fluctuation of the free energy are exactly like the fluctuation of the height of the KPZ equation, and these are Tracy-Widom distributed and so on. Now, what people does in practice, I would say you can study both, but I would say that many things are done with the directed polymer and then transferred to this model more than the opposite. Also the simulation and so on, most of the people will do it for this problem. But these two problems have an exact mapping, okay? They are exactly the same universality class. So what you are able to compute here, you can transfer it here and vice versa, okay? Okay, so this is not what we will do, but I just want to let you know. And now, let's continue with this problem. So now today we will study this problem. And a thing that I told you is that if H become time independent, then the solution you can write in a spectral form, because this is dtz minus h, which is time independent, times z. So z of xt is exponential minus th, okay? And then you have to impose the fact, so I will use what you have to impose, I will use what Abhishek did this morning. So you have to start at the position x, ends up at the position, sorry, start at 0 and ends up in x. And then you can, so now you have the exponential of an operator. So the best thing to do when you do the exponential of a matrix is to write in the basis of the eigenvector of this operator, which are the eigenstates of the Hamiltonian. And then you insert an identity here and here. And so at the end, you have the decomposition I wrote you yesterday, which is psi. So if the spectrum is discrete, you have this term. And when the spectrum is, the part of the spectrum is continuum with energy which are positive, okay, I don't know, infinity, rho e, psi, so these are typically wave function, not wave function, plane wave function, okay, the E star, E scatter, what is called scattering state, minus E of t, and then this is the density of state at this energy when you have the part of the spectrum which is continuum. So what you do usually when you have a quantum problem, if you have your Hamiltonian, you take the eigenvector problem, you discretize. If, for example, the potential is interacting, you will have a part of the spectrum, sorry, attractive. You will have a part of the spectrum which has bound states with negative energy, and then a part of the spectrum which is continuum. Okay, so this is what you have, but unfortunately we cannot use that because our Hamiltonian is non-time independent, so this is not true. Okay. Okay, so now what we'll do is, we cannot really do some progress using this equation. You can integrate numerically. This is what essentially was done by Ivan yesterday. But now, if you want to do some analytical progress, the only thing to do, and this is typical in disordered systems, you can compute the average of the moments of the partition function, which is the quantity that, I mean, we would like to characterize the statistic of the free energy, but we are obliged to do the moments of the partition function, and these moments can behave in a crazy way, and especially what can happen is that the second moment explodes compared to the first moment, and this means that the system is not, the partition function is not self-averaging. And so let's see what happens here. So, yeah. Yes, so let's say you can do both. Okay, there are people who do that, but typically most of the people will do the directed polymer, and then the free energy that you obtain is the interface KPZ. Okay, because you use this algorithm which is stable and is yes. So the people that compute the exponents usually use this one. Really simulate this equation, and the way it is done was shown by in this lattice model, as was shown yesterday by Ivan. Okay. So you put a model on the lattice, so you transform your Brownian motion in a random walk on a lattice, given disorder on the sides, and then you have this Dijkstra formula that allows you to compute either the ground state energy, if you want to work at t equal to 0, either if you want to work at t equal to fine, at t equal to 1, which is more in connection with this, then you use a kind of variant of the Dijkstra algorithm and you propagate this. So let's say that with t square, so if you have a polymer of length t, with t square operation, you know the free energy of your sample. Okay. Okay, so let me remind you what we told yesterday. So the first thing is that we choose a Gaussian potential. Okay, x1, tau 1, x2, tau 2. With zero mean, and here we said the disorder strength is delta, and delta correlated, so here it will be n if you want. Tau 1 minus tau 2. So these are the two average we will use a lot. And the second one is that if W is Gaussian, then you can ask what is the moment generating function of W. And essentially, for the Gaussian case, you have only the two first cumulants, okay, all the others are zero. And so it is something like this. Okay, so this is the formula we will use. And in our case, W average is equal to 0. So in our case, it's just exponential 1/2 W squared. Okay, for us, it will be always this formula. Okay, and then the other thing that maybe I want to recall, let me see where I should put that. So let me put it here. The third thing I want to recall is that Z3, okay, I also give you the way to derive, but okay, it's just the standard problem of diffusion. So in this case, so when I have the temperature T is exponential minus x squared divided 2tt 2 pi t. Okay, so is this, if we put v equal to 0 and you solve this equation, this is what you get. Okay. Okay. So now let's compute the first moment of z of x. What we have to do is take this, take the average over the disorder. And so at the beginning, we have our integral 0 xt equal x dx tau exponent. So we have the kinetic part, which is disorder independent, d tau x squared divided 2t. And then all the disorder is here. Okay. So we use this formula. So it will be exponential. We have to square it, so we have 2t squared. And then we have to square this. So we have tau 1 from 0 to t, 0t tau 2. Then we have Vx tau 1, Vx tau 2, tau 2. And we have to take this average. This is just d delta tau1 minus tau2, delta x1 minus delta x2, but x1, x2 are equal. So tau1 minus two are different. So one of the integral in tau goes away, but x1 and x2 are equal. So here we have a problem. Let me call this object delta 0, because this is a problem that comes from the continuum model. There is this divergence. But when you define the model on the lattice, there is a regularization that comes from the lattice. So it's not a delta peak. You have a random number on the lattice, and where you are on the same lattice, the variance is 1, it's not infinity. So this delta 0 is a regularization that comes from the lattice. The continuum model is ill-defined, just here, just for the first moment. You know that all lattice model that you will use, they will regularize this delta function. So there is no problem. Let's keep delta 0 here. And now if you do this integral, you see that you have exponential. So we have the d. 2, so I forgot there was 1/2 here. Okay, so the 2, why there is this 2, by the way? There is no 2, no? That's why. Yes, I put the 2, but in the wrong place, sorry. So the 2 is below. Okay, so we have d 2t squared. Then we have delta 0. And then we have to do this integral. There is a double integral in time. There is one delta function, so this integral is t. Okay? And so this is, so now this is independent on the path. So we can say that this is just d2t squared delta 0 t. And then we have to do this integral, okay? And this is z-free. So let me say that it's just z-free x t. Okay? So there is nothing special. The first model, we need to compute the second model to have information. But this is the integral, and is regularized by this delta 0. Okay? So now let's do the second moment. Let me remind you why we do the second moment. So I write here. So what we want to, at the end, look is this object. Okay, this object, if is 1, okay, then zxt is self-averaging. Annealed and quenched coincide, and essentially there is no strange phase. But if this is, there are two possibilities. One, then if it's small, there is nothing, maybe they don't coincide exactly annealed and quenched, but there is no phase transition. To have phase transition, if it goes to infinity, if it diverges with t, with the size of the system, then you have the glass transition. Glass phase, not transition, glass phase, okay? So there is a difference, strong difference between quenched and annealed, and you are dominated by these rate fluctuations, and so this is where you have the glass phase. Okay, so let's compute the second moment. So let me erase this, it was a recall. Okay, so here is where you introduce the replica, because you see that here we were integrating only on one path, but now when you do this, you have to integrate it over two paths. So this is the first replica. This is the second replica. And now we have a term which is the kinetic term that again is not very important in the sense that it's just d tau x1 square plus d tau x2 square, and from 0 to t. This nothing happens, there is no disorder, but the disorder is here. So let me write like this. We have the integral, so we have minus 1 over t, 0 to t, v x1 tau tau d tau minus 1 over t, integral from 0 to t, v x2 tau tau d tau. And this should be averaged over the disorder. Okay? So maybe. Okay, so we have to use again this formula. Again, the average is 0, but this we have to compute. So let's go. So we have 1/2. We have to compute now the average of the square of, let me write. So we have, okay, the minus 1 over t is with everybody. So let's put here 2t squared. And now we have the integral from 0 to t of v x1 tau tau plus the integral from 0 to t of v x2 tau tau tau. And this we have to do the square and to average. Okay? It's clear? This is only, I'm doing just 1/2 w square average. Okay? So this is what? So I have to take the square of this, the square of this, and then the double product. Okay? So when I take the square of this is exactly the calculation that I just did, because before it was just the square of v, okay? So when I take the square of this, I will have the same result. So it is 1 over 2t squared. So I have a term which is delta 0t, okay? I have this result. And then when I do the square of this, I will have still the same thing. Now what is different is the double product. Because now I have d tau 1, d tau 2, and then I have now two different replicas, x1 tau 1, v x2 tau 2. 0 t from 0 to t, and now I take the average. Okay? Now you see that this term is d delta n x1 minus x2 delta tau 1 minus tau 2. Okay? This is the average over these two v. And so you see that when you first apply the first delta, then these are replica acting exactly at the same time. Okay? And so But this now there is not an integral in X. So these two replica will remain interacting. And you have a term D, which is here. So at the end, when we write everything, we will have these two terms are identical. So the two disappear, is T delta 0 over T squared. And this term give you the factor 2 simplify. We have still a D T squared. But now we are, there is still a T. No, this T I don't understand. 1 second, what I did. Let me check. X tau 1, X tau 2. Don't get this. Oh no, it's correct. So sorry. I let it like this. So it's like this. So do you agree on that? So I let this integral. The replica are interacting at the same time, okay? And this is just dt squared, okay? The 2 is gone because there is the double product. So if I have to write now, this is the exponent of this exponential, okay? It's okay. So now I could just put it here or rewrite everything. So let me do this. I know that is not fair, but I don't know. So we have, so this exponential become now this. So we have a t square integral from 0 to t d tau delta n x1 tau minus x2 tau. And this term, I can put it here. Okay? Because it's not, doesn't depend on the path. Okay, now we can rewrite what is written here. So here I have an extra parenthesis, okay. So let me now rewrite the result well. So we have d delta 0 t square, which is the square of what I had here, okay, of the first moment. And then we have something which looks great. So we have two particles. Their path starts in 0 and ends up in x. This is x1. This is the particle number 2. And now we have something which is a kinetic term. So let me put it like this. The kinetic term, it will be d tau x1 square plus d tau x2 square. Okay, this is the kinetic part. And then we have the potential part. And the potential part is, maybe it's nice to write it here. So let's do like this. We have a minus. Here is 2 over t, 2 over t. And here we have a potential part, which has a sign minus, because there is a minus here. In order to have the plus, I have a minus here. And so this potential part is dt squared delta of n x1 tau minus x2 tau. Okay? So now it's written in a way in which I can write the Hamiltonian of this system. So where it is where I wrote this. Look, here I had the kinetic term, the potential term, and the Hamiltonian is written like this, okay? So you see that the potential V is the potential of the Hamiltonian, okay? So is this potential attractive or repulsive? Is my example here. So V of x is this one. So we see two things which are very important. First, do we have an explicit dependence on time now? No. So is a time-independent potential? And is attractive or repulsive? There is a sign, so D is positive, okay? So there is a sign minus, so is attractive, okay? Second important thing is attractive. So this is true always in disordered systems, and the idea is the following. We put two paths on the same disorder configuration, okay? The two replica are two paths on the same disorder configuration. And we integrate out the disorder, and these two replicas are attracting because they are seeing the same potential, and so they are somehow attracted, both of them, they are attracted to the low energy states, okay? So when you do the moments of the partition function, you integrate over the disorder, and then you have an interacting problem, and the replica are attractive, okay? And now we can actually use the spectral decomposition, okay? But because it's a simple two-particle problems, it is useful to go in the coordinates of the center of mass, just to have a better, easier way. So, so I can erase maybe this one. And maybe I can also erase this one, and I will let just the result there. So we are here. Okay. So now, so what I want to do is a simple thing, is just to introduce the center of mass coordinate and the difference between the two. So you will have that x1 is equal to capital X plus u over 2, and x2 is equal to capital X minus u over 2. And then you can write the cinetic term. So if you replace this, you will have this plus this. So, okay, let's do it. So you have the square of this the square of the other, then you have the double product, but here you have a double product with the plus, and here you have the double product with the minus, so then there is no double product. And then you have still the square of this one. So at the end, you have 2 times plus 1/2. Okay? So if you use this, you see that now you have essentially, okay, I can write. So you have now path capital X of tau. This path starts from 0. The center of mass starts in 0 and ends up in X. And here we have exponential, so there is a factor 2, so we have minus 1 over t d tau d tau x squared from 0 to t. Okay? And then we have times a new problem, which is the problem of the coordinate of the difference between the two positions. And the difference starts from 0, but because at the end both of the replicas goes in X, also ends up in 0. Now what you have here is exponential of minus, let's say now we can write it, I like to write in 2 pieces. So we have the integral from 0 to t d tau. We have d tau u square divided for t. And here we have minus d over t square v delta n of u. Okay? Did you follow? I mean, what I did is just change the coordinate between the center of mass and the relative coordinates. Okay? So now you see that for the capital X coordinates, there is no potential, it's free. So this is Z free. The only thing I should take care is that there is no 2 here. So there is, so it's like if, so there is no 2 here. And so what it means is there is no these 2, okay? So here I have exponential minus x squared divided capital T divided square root of p capital T. Okay? And what I can, so now the thing is, if I take, so if I go back to the one moment, this was, sorry, times Z free. So this is what you get for the the first moment. Now, if you compute what is Z3 square x t capital T, it will be exponential minus x squared divided t, and here you have something like 2 pi capital T. So you see that it's very similar to what I have here. There is just this square root factor, okay, that you have to match. So what you can do is that you can write that everything here is just like Z average x t square. And then I cannot cross here. Then you have, let me call this W of u equal to 0 t. So this is a new propagator. So times W u equal to 0 t. And then there is this division by, I think is 4 pi dt, which is the free propagator for a particle. I mean, if this is not there, this is what you have, okay? This is the factor you have. So this is not very important. What is nice is that you wrote the second moment of the partition function as the first moment squared times this object, okay? So if this object is W is divergent, then the second moment is much bigger than the first moment squared. And if it is bounded somehow, we don't have glassy physics, okay? So now let me maybe erase this. So what we have understood is that if you do Z square xt, okay, divided Z x t square, you have essentially this propagator from u0 to 0 to u to t to 0. So the part that go from 0 to 0, okay, du, and then we have the exponential of minus 1 over 4t integral dt d tau u square. And here we have plus, okay, you have to be careful that this plus means a minus at the end in the integral from 0 to t d tau delta n u tau. Okay, so the Hamiltonian of this system divided this square root of 4t pi. Okay, now the Hamiltonian of this object, it is t by 4 minus t by 4 Laplacian, and then we have minus dt square delta n of u. Okay, this is the Hamiltonian of my quantum particle. This is the kinetic term. This interaction term is a single particle of quantum mechanics in one dimension. The imaginary time is not very important. So now we have to solve the eigenstates of this problem. So what we know about a single particle with an external potential which is attractive in u equal to 0. So it means that your particle is free to go in u, except that is attracted by the point u equal to 0, okay? Do we have bound state or not? In general, do you know the answer? Yes, so in one dimension, so you see that the strength of this potential, sorry, there is a square here. So let me say, the potential we said is attractive. and the strength is d over t squared. So at high temperature is less attractive, at low temperature is more attractive. Okay, so the power of this potential depends on temperature. Okay, and so if you are in one dimension, do you have bound states? Always, no matter which weak attractive potential, always give you a bound state. So let's go and look at our spectral decomposition. A bound state has a negative energy. So at large time, when the polymer is very long, what dominates in this sum, in your opinion? So you have a bound state, you have a ground state, which is the most negative energy, and then you have a positive energy. So if you take big time, what is dominating? This term or this term? The ground state, no? Because it's negative, so the exponential is positive, it explodes in time. So at the end, if you have a bound state, so for, let's say, we know that not only in one dimension, but also in two dimensions, okay? For n equal 1 and 2, we always have a bound state, always. I know, it's not written like this. We have a bound state. And let's call it E0, the energy of the ground state. So what will happen is that z square xt divided z xt square goes like E modulus E0 t. So it explodes. So we will have a glass phase for all temperature. For any temperature, there is this bound state. So there is no pure phase. There is no free phase. I don't know. The polymer are always glued to the ground state. Okay. And then because with Ivan, you know that theta is positive, the exponent, okay, this I will say at the end in the summary, but essentially you have a glass phase. So I think Ivan did quickly because it was at the end, but if you measure the quench free energy, the anneal free energy of the polymer in 1D, in n equal to 1, it's always different, okay? Because it's always a glass. Now, the second thing, so let me erase here, is what happened above n equal to 2. Let's say, to be physical, n equal to 3. So what will happen? You can do simulation, you can observe everything in n equal to 3. So is a bound state always present in 3 dimensions? Or you need a certain strength of the potential? So above the 2 dimension, for the quantum particle with an attractive potential, okay, there is, let's say, a value Gc. So if d over t square is smaller than Gc, no bound state. Okay, so there is no bound state for high temperature, okay, because the potential is not strong enough and the Laplacian will win, okay? So you will have a delocalized state, and so you will have this term, and this term with positive energy will remain bounded, and so there is, let's say, a free phase, I don't know how to call it, but is a phase where the exponent zeta will be 1/2. It's like when you pick at random a polymer, okay? So let me call it free phase. The roughness exponent will be 1/2, okay? And the exponent theta will be 0. Then when you are above this strength, then the ground state appear. So at low temperature, you have a bound state. So you have a phase transition. So we have a glass phase. And what is interesting is that theta is bigger than 0. So it's measured. If you measure, so what I mean like this is that if you measure the fluctuation of the free energy at temperature, so let me write correctly. So let's say that you have your free energy, which is sample dependent. You measure the average value among all the samples. You do the square. It will be L power 2 theta, okay? And so this is true at any temperature, but actually depends on beta. And in the high temperature phase, so for beta, the high temperature means smaller than beta C, it will be 0. And for beta bigger than beta C, it will be positive. This is measured numerically, if you want, okay? So you have a transition in which the free energy at the beginning fluctuates of the order 1, and then, puff, it starts to fluctuate with a bigger exponent, okay? So this is a glass transition that you observe, let's say, when n is bigger than 2, okay? And when you are on the Cayley tree, it will remain 0 theta, okay? So, okay, this is what I want to say about the system, and now I would like to use the last half an hour to a little bit collect everything we had, okay? So, do you have question on this? Yes? Yes, so the physical hardware is in quantum mechanics. When you study the problem of one particle, okay, you have this potential. If you put any small attractive potential, you have a bound state in low dimension, while the Laplacian, so which try to delocalize your state, becomes stronger in higher dimension, and there is a theorem that says that the critical dimension is 2. Okay, so you expect that the behavior is that is more and more delocalized, you increase the dimension, and actually there is a critical dimension. So above 2, you always have, for small value of the attractive potential, you have no bound state, and so everything is free, it's just scattering states, while if you take a potential which is big enough, then you start to have a bound state always also in high dimension, but this critical value becomes higher and higher, okay?
I have one question. Here.
Yes. Yes.
Yeah, can I ask? So if we look at the complete picture, so we started yesterday by saying a random walk with starting from 0 and reaching a length. And then we model it as an effective potential. And then we are getting a attractive strength D here. So how will we go back from here? How will we look D from here to how the length is constructed? So how can we physically look at it?
Okay, so okay, the problem with the potential, so here we stop at the 2 replica calculation, okay? So the problem with the random potential, V, is more complicated, and if you want to really find the result, the correct value of zeta and theta, then you have to compute all the moments, so zeta cube, zeta 4, zeta n, so for generic n, and then this model in quantum mechanics, when you integrate over the disorder, become a model of n particles with delta potential, which is called Liebniger, is integrable. And for this reason, in 1D, you are able to solve it. But let's say like this. So just the physical intuition is the following, is that when you integrate, so the two paths are free, but they go on a same potential. So this potential will have valley, which are the same. So these two paths we will have a tendency, will have a gain to go in the same valley, so to be attracted by the same valley. So when you integrate out the potential, you don't have anymore the same problem as before. Actually, it's a simpler problem because it doesn't capture all the original problem. But the potential is attractive to translate the fact that these two paths, which were free, now because they were seeing the same external potential, in absence of this potential, they attract each other, okay? Because they were seeing the same value, okay? Yes?
V, the V potential random variable we choose. So what is the role of that V to this D?
So, okay, so the calculation I've done strongly rely on the Gaussianity, because if the V was not Gaussian, you cannot use all this Wick technique. You cannot do the average of exponential of V easily. So there is most of the work which is done analytically is done with Gaussian potential in order to use this formula, which was the key to compute the moments of the partition function. However, in the simulation, you see that no matter which potential you use, at the end, the long distance property are independent of this potential. If you replace Gaussian with uniform distribution or with, I don't know, exponential distribution, you will find the same zeta, the same theta, and so on. So the results are independent. I mean, some of the results, the universal one, are independent on the nature of the disorder, but for the analytical calculation, you have to use the Gaussian.
So the only constraint we have is they both should end at the same point. Start at the same point, end at the same point.
Yes, so the paths are, so so when you do the replica calculation, when you do Z square, before the integration, the potential of the two replica, so you have two independent replica, but which are sitting on the same potential. This is the key point. They are sitting on the same potential. Then you integrate out the potential and these replicas start to attract.
Okay, thank you.
Okay, so let me try to make a conclusion. So what I need is not this. No, actually it's nothing. I will erase everything. Okay. So let me recall you that, okay, in the, so let me recall you that we saw, let's go back to the RAM now, okay? So what I told you is that essentially the fluctuation, so if you stay at 0 temperature, okay, you look the fluctuation of the minimum, say minus AM, so let's say typical minimum, okay. So you look at this, what you have some BM, okay. I call this, actually this will be, let me do correctly, like this, and then take the square root. This is BM. So BM give you the size of the fluctuation of the minimum. And then we said this is very interesting because it doesn't give only the size of the fluctuation of the minimum, but now if we define n of x, which is the number of states. So let's have the minimum here. So I have my realization. Then I take some value x in the energy. So these are the energies. Okay, let me write here. These are the energies which are sorted. Okay, so this is the smallest energy. And then I have other energy levels. Okay. And so I want to count how many of them are between E min and E min plus x. So this I did in the tutorial, and I told you, actually, you can compute this using the same extreme value statistics. And what you will have is that this is something like this. This is the ground state. This is the number of states above the ground state up to x. So this number grows with x, but you see that if you fluctuate a lot, this number decreases. So B of M give you also this. So the biggest is the bigger are the fluctuation, the less the states you have in the RAM close to the minima. Okay, and so in the RAM, this BM. Now I don't remember if it's square root of log 2 or. Yes, it's beta C. So yes, 1 over Bm is beta C. So this Bm is 1 over square root of 2 log 2. This is in the RAM, okay? So it's a number of the order 1, and is not growing with the system size. So now this allows us to see what is going on in these glassy phases, okay? So let's say that we have the partition function, Z. So let me call Z alpha the Boltzmann weight associated to a given configuration alpha. So you pick one of the random number, and this is its Boltzmann weight. So when you sum all of them, you have the partition function, and you can compare this to the energy of the ground state. Is this explosive, in which case the ground state has no particular, its weight is negligible, so there is no condensation, or if it's finite, it means that there is condensation. So let's look what we have. So among all the states, there is the ground state, so let's put it 1. And then we have the sum over alpha different from the ground state. And this is exponential minus beta E minus the energy of the ground state. This is what we call X, okay? And so we can transform this sum in an integral from 0 to infinity in dx. And here what I have to put is, so n is the total number up to x. So if I want the number I have at x, I have to take the derivative. And then I have exponential minus beta x. Okay? So if I take the derivative, now I use the results we have, is exponential of x 1 over bm minus beta divided bm. Okay, and now we have seen that I recall you that beta c is 1 over bm. So I can use this notation, and so this will become beta c, and this becomes beta c. Now we have two possibilities. If beta is smaller than beta c, I mean the high temperature phase, this integral diverges, okay? And this means that the partition function is huge compared to the ground state, the weight of the ground state. So the weight of the ground state is one of the weight among the 2 power n states, so there is no condensation. I'm in the free phase, okay? Now, for beta bigger than beta c, the result is finite, is 1 plus beta c divided, so this is beta bigger than beta c, divided beta minus beta c, okay? So it means that only the ground state is a fraction of all the Gibbs measure. So it means that you spend a finite time on, imagine you do your Monte Carlo perfect, where each time you pick one configuration from this measure, okay? And then it will happen with finite probability that you pick the ground state. This is huge. It means that the ground state has a huge weight because there are 2 power n configurations. And so there is condensation on top of the ground state. So at the question, in the glass phase, which is this one, do I have a probability to pick 2 times the same configuration? The answer is yes. So this is what happens in the glass phase. You pick configurations that are very similar, okay? While in the ground state, you pick configurations that are always very different. And so for this, it is useful to define the overlap. So I will define for the spin problem, but you can define for the polymer. The overlap is the common path of the 2 free paths. So let's say that you pick 2 configurations, alpha and gamma, okay? And now they have, so this is the number of spin. So you have I from 1 to the number of spin. And is sigma alpha I, sigma I gamma. So you look at the spin if they have the same sign or not, okay? And so this tells you if the 2 configurations are similar or not, and is normalized to this value. So now let's imagine first in the case of the Ising model. So if you pick 2 configurations from the paramagnetic phase, beta bigger than, no, paramagnetic is beta smaller than beta c. If you are a paramagnet, okay, the spin are equally probably plus and minus. So this sum will be of the order square root of n. Divided by n, it will be 0 in the limit n goes to 0, okay? So you can do this game of picking configuration from the Gibbs ensemble, making the overlap between them, and what you will see is that P of Q, when n goes to infinity, is delta of Q. Essentially, they are different, okay? They have a small overlap, but divided by n, it goes to 0, okay? Now, for beta bigger than beta c, okay, first I give you the result of the REM. I didn't show that, okay? But we know that there is a finite probability to pick again the same configuration. So there is this ansatz, which is correct. You have 2 delta peak. This is the ansatz, okay? And the weight and the position of the 2 delta peak that can depend of the model, okay? For the REM, it is delta Q of 0 beta c over beta. And here you have 1 minus beta c over beta, delta 1 minus Q. So in the REM, you have only 2 possibilities. Either you pick 2 different configurations, because in any case is an uncorrelated model, so there is no particular structure. So in this case, they are completely different. Or there is a finite probability to pick the same configuration, okay? Now, what is the peculiarity of the REM, of this model in mean field in general, is that the number of states which are at low energy, they all have this Bose-Einstein condensation. It's not only the one, the ground state. So there are a number of states that contributes to this peak, okay? So let me explain the things like this. So let's go back to the example of the ferromagnetic transition, okay? So if you are in a ferromagnet, what will happen? For beta smaller than beta C, you are a paramagnet, so you will have P of Q equal delta of Q. Now, what happens when you become a ferromagnet? The configuration, okay, they are or with a positive magnetization or with a negative magnetization. There are two states, which we usually, in this language, we call pure states. There are two states that have opposite magnetization, okay? So if you pick configuration that have the same magnetization, okay, you will have something like delta Q minus m square with some weight, mu1, okay, it will be more or less 1/2. And then with the weight 1 minus mu1, you will have the other peak will be plus m squared. So the configuration either are both positive and both negative, in which case you are in this peak. Either they have opposite sign, in which case you are in this peak. So you have two minima which are more or less the same energy, but they are related by a symmetry because it's not a frustrated system. So there is a geometrical order. You can, given one of the minima, you just change sign and you have the other minima, okay? Here is different because now you don't have to think to the RAM, you think about the spin system. You imagine to be able to do the ground states, and all the states are small energy, which have a very similar energy, which fluctuates of small quantity of the order 1. And then what you have is that they are all ground state in some sense, but they are very different geometrically. So when you make the overlap between one state coming from one minima and the other state coming from the other minima, you don't have this peak because it's not related by a simple symmetry, but you have this peak. So what it means is when you are in the glassy phase, the state of the system start to be attracted by minima, start to condensate by few minima. So the entropy goes to 0, at least the configurational length goes to 0. And then either you pick the two configurations from the same minima, which contributes to this peak, either you pick from two different minima, but because they are very different geometrically, their overlap is 0. Okay? This is what happens in one step. And now, okay, so this is what happens. And so what I told you is the simplest version of the mean field spin glasses are the one with only two delta peak, the RAM, the directed polymer on the Cayley tree, the pure p-spin model, they are all in this category. What can happen more complicated is what is called the full replica symmetry breaking, in which case your system, so imagine that this is the phase space, okay? You start to have this minima, okay? But then a feature. There's not written I'm the ground state, but still they are few, and then you start to see that they are similar, or they can be distributed to count how many you have in the low temperature phase. So this is all for the mean field model. So that's what we do for the finite system, for the final dimensional. So in the final dimension, the things are much less clear. Let's say that this, what I told you now, are the two mechanisms for the glass transition in all mean field models. Now what happens in finite dimension is less clear. So, and again, what you can measure is the fluctuation of the ground state. And so what you can have are the following things. Either, so I didn't discuss, when theta is negative, when this fluctuation becomes very small, it means that you have a huge amount of states close to the ground state, so there is no phase transition and no glassy phase. So this is the case of the 2D or 1D Edwards-Anderson model. They don't have glass transition. The disorder somehow is irrelevant. There are interesting features, but it's not. Then you can have, we have seen that theta could be bigger than 0, 1/3 in the directed polymer in one dimension. And then two things, we have seen two things. For n equal 1 and 2 in the directed polymer in random media, we have seen that there is only the glassy phase. But here, at variance, what happens there, the P of Q is delta 1 minus Q. So there is only the ground state. So the theta is positive. So it means that to make an exit, I told you that this is at least give you the idea how are the excitation. So if you do an excitation which reorganize a little bit of the polymer, it will be at low energy of the ground state. But if you do an excitation which reorganize a lot the ground state, it will cost a lot of energy. So we'll not visit this one. So the only state which is the minimum is the only ground state is unique, and all the excitation are on top of it. So they are finite size excitation, you don't have the peak. So there are people who are fighting a lot on the glassy phase, and essentially they try to detect if there is this peak or not, okay, in most of the cases. So if it is unique, it's like this, or we have seen that in n equal 3, 4, then there is a transition, Tc, but is not RSB, is not replica symmetry breaking, but is more of this kind. So in the glassy phase, you are still attracted by a unique ground state. So there is at least one case where you know that you're not attracted in. And then the question is what happens in general, and I will not answer to this. So I mean, there are a lot of discussion. So I want to show what are the two systems we understand quite well. Let me mention that I also mentioned the case of theta equal to 0. Then this is for the Cayley tree, okay? When theta is equal to 0, I think you will have the RSB physics. But the problem is to find a model with theta equal to 0 in finite dimension, okay? Okay, so essentially when you are glass, there are two ways you can become glass. Either you have many ground states, okay? And this is where there is the trick of Parisi that works, and this trick allows you to extract the information of the free energy from the moments of the partition function. Is a variational approach, which works and allows you to make enhancements and see that the free energy you get is the correct one. Or for the other word, there is no really power. There is one case which is integrable, is this case n equal to 1. So here you can really study everything, but already starting from n equal to 2, you can do z cube, but then you cannot really make progress at all n, okay? So this is the end. I think I told you everything I was planning to say. And tomorrow we will start to do another subject completely different, okay? Okay. Yes.
In this case, where we are saying that there is one ground state where most of the configuration will go and sit, then how do we connect it to the picture of the glassy systems where we say that there are many?
And then what you will see are things like this. So this, you pick a random configuration and you will see a configuration. This is a random configuration at t equal to 1, okay? So you have some droplets which you can construct, okay? You can predict the size of these droplets depending on the temperature. So this is one, then you pick the other one, it will be maybe like this. Okay, but you see they are very different from a random configuration. They are stick on the ground state. And you will never see a configuration like this. I should change color. So at t equal to 1, you will never see a configuration like this. You will always see excitation on top of the ground state. There are plenty of excitation. There will be many configurations, but you will always see that they are fluctuating around the ground state. In a mean-field glassy system, it's more tricky to do the, for example, if you use, just to give you an example, if you use the Cayley tree, then imagine the ground state is this one. And then you do the same game. You pick at random at temperature t equal to 1, below the critical temperature, okay? You pick at random a configuration. And so sometimes you will pick configuration like this, or like this, okay? But sometimes you will pick a configuration which is like this. And this you can really see, and you see the difference. So it means that in this system, there are many ground states. There is a unique ground state, but the others are a small energy above. So among the excitation, there are excitations which are very different from the ground state, while in this case, no. There is only this one. So they are all glassy, but the glass transition if you find most of the people that talk about glass transition work in mean-field glasses, and so they will they always have in mind this mechanism and the RSB solution. Okay.
So this is typically the property of this model system.
Let's say if you have a glass transition in mean-field system, there will be this feature. If you have a mean-field system, there will be this feature. In the finite system, I don't know in general. In this system, there will be no this feature. Okay.
Thank you.